Hello everyone. Our next unit is going to be on angular motion. Now angular motion is not the same thing as linear motion. A linear motion is when we move along a path. Angular motion is actually considering something that's spinning. And we've looked at uniform circular motion where something travels around in a circle, but in angular motion we're actually more interested in about the thing that is traveling in a circle. So here I have like a disk that is spinning. And yes, it has what we call tangential velocity, which is what these arrows are showing, but it also is actually moving around its own axis of rotation, and this thing is spinning. Now if you notice, the outside of this is going to cover a distance equal to its circumference, and the inside of it is going to cover a distance equal to its circumference in one revolution, which means the outside of it's actually got a higher linear velocity than the inside of it, but they both go one revolution in the same amount of time. So that's what these angular quantities are. And if we take a look at what that means, we're looking right here. As this disk rotates around its axis of rotation, it's moving this way. This point that started here ends up over here. It's changed its angular position, right? If we're calling this axis right here, this line, the 0 position mark, then as this thing spins, this part of it rotates through that angle. And every part of it has actually subtended that same angle. So when we're talking about angular motion, we're actually talking about things spinning around an axis. It may be easy to consider this if we think about a tire. If we have a tire, it moves along the ground, but it also spins. So down here, we have the ground, and as the tire moves along the ground, we can think of this point on the tire. It's here, it's in contact with the ground, and then it's going to roll, and this point is going to come down in contact with the ground, and this arc length that it covers is equal to the distance that this thing moves across the ground. So we have our axis of rotation here where this tire is spinning around, but it's also moving translationally or linearly along the ground. So what we can look at is we could look at the linear displacement as the center, this axis of rotation moves from here to here, but we can also look at the angular displacement when this part of the tire rotates from here down to the bottom part of the tire. And this displacement is what we call the angle theta. It's the angular displacement. We're going to measure that in radians, and then we could talk about how fast that happens in radians per second, or how fast that is accelerating in radians per second. So as this tire actually, like if this car is speeding up from rest, this thing is speeding up around that circle as well. So we have angular motion, the spinning of the tire, that goes along with the linear motion as this thing rolls along the ground. So we're going to be investigating how this angular motion stuff works. And it's really not any different. We analyze it in a very similar way as the linear motion. So we have our three kinematic equations. Remember, our first kinematic equation that we had for linear motion was the change in position. Actually, that's not our first one. Our first kinematic equation that we had was our change in velocity, or our final velocity, is equal to the initial velocity we started with plus acceleration times time. We're going to see the rotational analog of that. Okay, our second kinematic equation was our change in position, or our final position, is given by 1/2 the acceleration times time squared plus the initial velocity times time plus the initial position, right? Sometimes we write this as delta x equals 1/2 at squared plus v naught t. And remember, that's just as this thing moves from one position to another. Here's x, here's, or x naught, here's x, then this is delta x. Right? And our third kinematic equation, if we take this, solve it for a, sub it into this equation, we get v squared equals v naught squared plus twice the acceleration times the change in position. So those are the three linear kinematic equations, and we're going to go ahead and we're going to derive their rotational or angular analogs in this next section. So sometimes you'll hear me refer to it as rotational, sometimes you'll hear me refer to it as angular. Those are essentially saying the same thing, right? Instead of having an angular displacement, we're going to have something that rotates through an angle, and so that's rotational motion that gives us angular displacement.